Hey AP Chem, today we're gonna go over the section 5.4 guided reading notes, and I will also provide you answers to the 6.5 worksheet. So I'll run through those answers. Later this week we will do a Google Meet so you can ask questions and everything, but that way you have answers and you can try again if you got anything wrong. Pepin's right here sleeping in his bed, so have no fear, he's here with us. Right, puppy? He's sleeping. Alright. So, section 5.4, enthalpies of reaction. The mathematical equation for enthalpy change is going to be delta H, which is enthalpy change, minus the H, or enthalpy of products, minus H of reactants. When you see the, ooh, gotta scroll weird, there we go. When you see the symbol delta H of reaction, the letters RXN are an abbreviation for reaction. And I've kind of used that before, but now you know. It is important that the value of H of reaction has a sign. A positive sign means that the reaction is endothermic, and negative sign means the reaction is exothermic. And then this is just a reminder here saying a balanced chemical equation that shows the associated enthalpy change is called thermochemical equation. The guidelines on page 174 are helpful when using thermochemical equations and energy diagrams. Okay, then number 4, we have enthalpy is an extensive property. The magnitude of H is proportional to the amount of reactant consumed in the process. So remember, there's intensive and extensive properties. Intensive do not depend on how much of a substance you have. So things like density, grams per liter or grams per volume, mass over volume, that's an intensive property. It doesn't change. Same thing with like color. Doesn't matter how much you have, that color doesn't change. Extensive properties do depend on the amount that you have of a substance. Number 5, the enthalpy change for a certain chemical reaction is equal in magnitude but opposite in sign to the delta H for the reverse reaction. 6, the enthalpy change for a reaction depends on the states for the reactions and products, such as solid, liquid, and gas. Okay, then we have a problem here. Complete combustion of ethanol to form H2O and CO2 at constant pressure releases 1,235 kilojoules of heat per mole of C2H5OH. First part, write a balanced thermochemical equation for this reaction. So we'll see if I can use this screen brush thing. It's not the best, but whatever works during these times. So, of course, our reactants are going to be C2H, oh man, that's bad, 5OH. Also disappeared, which is annoying. I can't fix it, I'm sorry. We're also going to have, since it's combustion reaction, it's going to be plus O2. This is just bad. Okay, and then our two products are going to be H2O and CO2. In terms of coefficients, we have a 1 in front of ethanol, a 3 in front of O2, a 3 in front of H2O on the product side, and a 2 in front of CO2. Okay, so those are our coefficients. Then, of course, the delta H for that reaction is going to be negative 1, 2, 3, 5. Oh, 3, 5. And then our unit for that is going to be kilojoules per mole of reaction. Okay, so sometimes you'll see just kilojoules per mole, but you'll also see kilojoules per mole of reaction. That tells you that in that equation, since all the coefficients are kind of different, like they're not all 1-to-1, we say mole per reaction. So if we have 1 mole of ethanol, 3 moles of 3 moles of O2, producing 3 moles of H2O and 2 moles of CO2, that would be how many kilojoules were released per mole of reaction. So you have to have those specific ratios in order for this much heat to be released. Part B says draw an enthalpy diagram for the reaction, similar to figure 5. I think it's supposed to be 5.16 or figure 5.14. Okay. So, since we have heat being released, that means that our products are going to be at a lower energy level than our reactants. So we're going to have our reactants up here, the C2H5OH, and the products down here, CO2 and H2O. Then going from reactants to products is going to be negative, and then our delta H would then be negative 1235 kilojoules. Going the opposite direction from products to reactants, the reverse reaction would be positive 1235 kilojoules per mole. And then I need to close this apparently to scroll. Quit. There we go. All right. Then we have another problem. We have the decomp of slaked lime, CaOH2, into lime, CaO, and H2O gas at constant pressure. It requires the addition of 109 kilojoules of heat per mole of this slaked lime. First part, write a balanced thermochemical equation for this reaction. So here, since this is a decomp reaction, we only have one reactant, and that is CaOH2. And it is breaking down, so on our product side, we're going to have CaO and H2O. For all of these, the coefficient is just going to be 1, so it's 1 to 1 to 1, so we don't have to adjust coefficients. And then our delta H is going to be positive this time because it requires the addition of 109 kilojoules for every mole of reaction. For this time, the products are going to be, well, let me write on here. Oh, no, oh man. Ooh, I bet I do have a highlighter. Maybe? Oh, I can only highlight that. Okay, sorry. I'm just still playing around. It's fine. What about this one? No, that's the signature. Edit text and images. Yeah, no. Okay. This time, anyhow, our products are going to be at the top. They're going to have a higher energy level than our reactants. Okay, so we're going to have products up here, reactants down here. So then our reaction from reactants to products is going to have positive 109 kilojoules. Going from products to reactants, it would be negative 109 kilojoules per mole of reaction. Hopefully that helps. I wish I could mark up. It's just different programs are not great. Okay, number 9, the thermite reaction is shown on figure 5.8 on page 168. Aluminum reacts with iron 3 oxide to produce aluminum oxide and iron. Write the balanced chemical equation for this. So we should have, for our reactants, we should have 2 aluminum solid plus Fe2O3 solid, yielding Al2O3 solid and 2 Fe solid. So we have aluminum plus iron 3 oxide yielding aluminum oxide and iron, and we have a coefficient of 2 in front of aluminum and iron. Based on the information in figure 8, what's the sign of delta H for this reaction? So if you look at the image, you see a lot of fire, explosion, heat. That's negative because it's exothermic. Here we say the thermite reaction releases 848 kilojoules of heat for every 1 mole of iron 3 oxide that reacts. How much heat is released when 1 gram of iron 3 oxide reacts with excess aluminum? Show the setup for this calculation, which also involves 2 conversion factors. So what we know is that we are reacting 1 gram of iron 3 oxide. So we are going to have 1 gram, and then we're going to have to convert to moles because it's kilojoules per mole. So to do that, we multiply by 1 mole over the molar mass of iron 3 oxide, which is about 158.7 grams. And then we multiply by 848 kilojoules over 1 mole. So if you plug that in, 1 gram divided by 159.7 times 848 divided by 1, it's going to be equal to 5.31 kilojoules that are released. You don't have to put the negative sign because they're just asking for the amount of heat. They're not asking for the delta H of the reaction. If they ask for delta H, you would want to put the negative sign, but you can also think like they say how much heat is released, so you know it's negative, basically. Okay, so again, it should be 5.31 kilojoules released. Part B, if we have 1,750 kilojoules released, how many grams of iron are produced? So this way we're kind of working backwards. So if we have, I'm going to use negative signs this time, we have negative 1,750 kilojoules. We're going to figure out basically the mole ratio for this reaction. So I'm going to multiply by basically the inverse of 848 kilojoules per mole. I'm going to multiply 1,750 times 1 mole divided by negative 848. Again, negative because we know it's released in the overall reaction. Then, in our balanced chemical equation, we have 2 moles of iron for every mole of reaction that's produced. So we take the coefficient of iron, 2, for every 1 reaction that's occurring, and then we multiply by the molar mass of iron, 55.845 grams. And we get 230.5 or 231 grams of iron that were produced. So again, our setup is going to be negative 1,750 times 1 mole over negative 848 kilojoules times 2 moles of iron for every 1 mole of reaction times 55.845 grams for every 1 mole, which is the molar mass of iron, and we should get about 230.5 or 231 grams. Based on the information above, determine the delta H value for the following reactions. So in A, you notice every coefficient is doubled, okay? So this delta H reaction is dependent on the amount of reactants and products. So, since we have double, all that we do is we multiply this negative 890 by 2, so you should get delta H equals negative 1780, so 1,780 kilojoules. Here, what you'll notice is that we have basically the same reaction, but it's reversed. Our reactants are on the product side, and our products are on the reactant side. So basically, we've flipped this. We've done the reverse reaction, which means all that we have to do is flip the sign of delta H, so we get positive 890. 13, the value of delta H is not equal to negative 890 kilojoules. Explain. There's only one difference between this reaction and this reaction up here, and as up here we have liquid water, and down here we have gaseous water, okay? So the state of water in this reaction is gas, not liquid, and the enthalpy change for a reaction depends on the states for reactants and products. So since H2O gas is a different state than H2O liquid, our enthalpy change is going to be different. 14, decide if the magnitude should be larger than or smaller than 890. Draw an enthalpy diagram to justify your answer. It will be less because heat is available to transfer to the surroundings. So you can kind of think of it like to go from liquid water to gaseous water, it takes energy. So rather than inputting energy to the surroundings, what's happening is it's inputting energy to a phase change. So we're going to have less heat released to the environment. So our enthalpy diagram, you can like request to see this if you want me to do it on the whiteboard. But basically we're going to have our reactants CH4O2 up here, products CO2 and H2O liquid down here. Since H2O gas has more energy, it's in the enthalpy diagram, it would be up kind of between the two, which is why our delta H would be less. Okay. 15, we have hydrogen peroxide decomposing. Write a balanced chemical equation. That balanced chemical equation looks like 2 H2O2 liquid yielding 2 H2O liquid plus O2 gas. So we have a 2 coefficient for H2O2 and a 2 coefficient for liquid. Calculate the delta H for the reaction written in part A. We're going to take the 5 grams of H2O2, convert it to moles by dividing by the molar mass, which is 34.014. Then you get about 0.147 moles Then we're going to divide the kilojoules release, 14.4, divided by 0.047 moles, and that equals 97.96 kilojoules per mole of H2O2.